This video is going to cover sections 1.5 and 1.6. This is about vectors and how to add and subtract vectors. So first of all quantities that can be measured are grouped into two categories, a scalar or a vector. So a scalar is something that you can describe with just a number. We say that a scalar has only a magnitude. Magnitude is just another word that means size. So for instance, a temperature can be described just with a number. It can be 20 degrees Celsius. A speed or a mass, those are all scalars. Vectors, on the other hand, are things that have not only a magnitude or a size, but they also have a direction. So here's some examples of things with that are vectors. Now, a lot of people use speed and velocity interchangeably, but by definition, the difference between speed and velocity is that velocity also has a direction. So speed might be given as 5 miles per hour, and that fully describes the object's speed, how fast it's going, whereas velocity would have to be given as 5 miles per hour north, for instance. So this is a velocity because it includes a direction. This does not. That makes this a vector and this a scalar. Okay, so we represent vectors using arrows. That's convenient because we can easily show the direction with the arrow, and we can represent the size of the vector quantity by the length of the arrow. So when you're drawing a vector to represent a quantity, the size should be proportionate to the magnitude of the vector. So here we have a force of 4 pounds, and in the same direction a force of 8 pounds. So since this one is twice as big, our representative arrow is twice as long. We also need a way to describe the direction. So it's easy if the vector just points straight north, south, east, or west, or straight up and down or side to side. But often we have vectors that point somewhere in between. So for instance, using this coordinate system, north, south, east, west, this vector points somewhere in between north and east, but it's not specific enough just to say northeast. In fact, if you say northeast, that's implying that you're exactly between north and east. That would make this angle 45 degrees. But our angle is not 45 degrees, it's 30, so we're a little bit closer to east than we are to north. So the way that we describe this is whatever direction this is closest to, we look at that direction, so this would be east, and the other direction. So basically the two directions that it's between. Let me draw my arrows here. So this would be east, this would be north. So it's between north and east. So we would describe this as 30 degrees north of east. So we're not quite going east, we're going a little bit north of there. How much north of there? 30 degrees north. This technique can also be used with other coordinate systems where you might be dealing with left and right, up and down. So not looking at a map, but here where this is up, down, left, and right. You can use the same idea, but here this would be, if this was a 30-degree angle again, that would be described as 30 degrees above the horizontal. Let me write that somewhere else. Above the horizontal. Okay. You could also describe that with reference to the other direction. So this angle. If you wanted to measure this angle, those two together have to make 90, so this angle would be 60. How do we describe that? That would be 60 degrees from the vertical. Okay, so either one of those would be acceptable. Alright, so if we want to add two vector quantities together, we use a technique called tip to tail, or here they're calling it tail to head, head being the tip of the arrow. So if you have two vectors that are already pointing in the same direction, it's very easy to see that if you place them, the tail of one vector at the head of the first vector, you're basically just adding them together. So here's an example. If we have a 5-meter vector plus a 3-meter vector in the same direction, we get one big vector that's 8 meters in that direction. It becomes a little more tricky if you have two vectors that you're adding which are not in the same direction. So for instance, let's say this first vector was headed east and then we turned and headed north. Now if this was 5 and this was 3 again, our total distance that we've traveled between the start and the finish is not going to be 8. So r is not now equal to 8. So to figure out what this is, we have to use our trigonometry that we looked at in the last section. So notice again, we're just placing the tail of the second vector where the tip of the first one leaves off. So here's an example, 6 meters plus 2 meters. So the total of these two is not going to be 8 meters. It's going to be this side of the triangle. This is called the resultant. And that's why they have it labeled as R here. That stands for resultant. And that just means the total of the two vectors. Alright, so if we wanted to find that, we could just use the Pythagorean theorem because these two make a nice right angle here. So we have a right triangle, this would be the hypotenuse, these would be the legs, and we could solve for the resultant. One interesting thing about vector addition is that it does not matter what order you add the vectors in. So this was A, and this was our vector B. We could add them in the opposite order as well. If we drew B first, I'll try to draw this somewhat to the same scale. So let's say we put B first. Then we would have to start vector A where B leaves off. So then vector A would start here. That would be A. So then what we do is we draw our resultant pointing from the starting point where we started our first vector and to the ending point. So it would point from here, the start of B, to the end of our last vector that we drew. And we would label that R. Now if you notice, taking into account my shaky lines, this R is exactly the same as this resultant here. So it doesn't matter if you draw A first then B or B first then A. You still get the same resultant. It's the same size and it's in the same direction. So here's that problem worked out using the Pythagorean theorem. Okay, we also need to describe the angle. In order to describe this resultant vector fully, we not only need the length or the magnitude, we also need the angle. So here we can find the angle using our SOHCAHTOA. So we could, since we know each side now, we could use any of those, sine, cosine, or tangent. But it's probably best to use tangent. So remember, TOA stands for tangent theta equals opposite over adjacent. So if this is our theta here, then our opposite side would be 2 and the adjacent side would be 6. And if we choose these two to use, we're using numbers that were given in the problem as opposed to using a number that we calculated. So this is a better method. Just in case we made a mistake calculating this number, we'll still get the correct answer for theta if we use tangent, which uses these two numbers. So you can see this set up here, and we get an angle of 18.4 degrees. Now since we have a diagram here where theta is clearly labeled, we don't need to describe the direction. But if we wanted to, we could say this is above the horizontal, assuming this is vertical and this is horizontal. Alright, it gets a little trickier when we have vectors that are not at right angles to each other. So here we have to do something called vector resolution, and we'll talk about that in the next video.